higher dimensions. And for the conical singularity, this alpha parameterizes the angle deficit. In this case, alpha squared is positive, and we see if we add more mass in our space, this alpha goes to be imaginary, pure imaginary, and then this next singularity of conical singularity evolves to the BTZ black hole, and the singularity is now covered by horizon. In the case of the conical singularity, the corresponding metric in the bulk is given by this expression, and we see that the metric coefficients depend only on the radius, and it means precisely that we can do a partial Hamiltonian reduction and restrict the dynamics to the two-dimensional slice of three-dimensional geometry, and this two-dimensional slice has negative curvature, and in fact this is just a Poincare disk. So in this picture we see that two background heavy operators create background bulk geometry, while perturbative heavy operators correspond to test particles propagating in this geometry, so that the world lines form a particular network of geodesic segments. And on this picture, this network is depicted here on this two-dimensional Poincare disk, and the points Wi's correspond to boundary attachment of the external legs of the original conformal block. So we claim that the linearized conformal block up to global conformal transformation is equivalent to the length of this geodesic graph, where the length is composed of lengths of different segments here, so that this sum is minimal. This is why we call this network geodesic. And these two functions, modular conformal transformation, coincide. There is a simple mnemonic rule which helps us to build this geodesic network for given conformal block diagram, and to this end we draw in black these two rightmost operators, so they're heavy background operators, while other lines correspond to heavy perturbative operators, including exchange channels. And then we just erase these two rightmost operators, and the remaining diagram should be inserted into the two-dimensional disk, so that this endpoint goes to the center of the disk, while endpoints of the external legs are attached to this boundary circle, which is the conformal boundary. Now we claim that modular conformal transformations, these two functions, linearized block and the length, are equal to each other. I should say that in the endpoint case, these functions are not explicitly known, because finding them is a very complicated problem related to solving a system of algebraic equations. But there is the existing theorem claiming that under appropriate conditions, and we don't know how to find these functions explicitly, these left-hand side and right-hand side should coincide. So this relation provides the semi-classical additivity correspondence in this case. Okay, now we turn to the torus case, and of course our primary goal is to extend this block length correspondence from the sphere to arbitrary Riemannian surfaces. And the torus case here is the first non-trivial case. It corresponds to the Riemannian surface of genus 1. And I should say that contrary to the sphere case, 0-point function and 1-point function are quite non-trivial functions on a torus. For example, 0-point function is just a Virasoro character, while 1-point function is as much complicated as 4-point function on a sphere. Moreover, these authors claim that there is a map between one-point torus function and four-point sphere function. So, I mean that one-point torus blocks are quite non-trivial functions to study, and in general, I would like to say that classical conformal blocks are very poorly understood, except for sphere case maybe. And in this respect, I would like, poorly understood for arbitrary genus G, arbitrary Riemannian surface, and arbitrary number of operator insertions, that is in the endpoint case. And in this respect, I would like to note a recent interesting paper by these authors who claim that they have a general calculation scheme to find Virasoro quantum blocks, and possibly that will help us to find the corresponding classical conformal blocks. So we see that classical conformal blocks is just a kind of terra incognita for two-dimensional conformal field theory. Okay, and let's now consider one-point torus block, and by analogy with the sphere case, it's defined as a holomorphic part of one-point correlation functions living on a torus for some primary operator with conformal dimension delta. Here it's just a structure constant. It is model dependent, and conformal block is model independent. It's completely fixed by Virasoro symmetry, and conformal block on the torus is given by this power series in the modular parameter Q, which is related to the modulus of the torus tau. And the expansion coefficients here are given by these matrix elements of the primary operator, where prime ket vectors are given in a standard way by acting with Virasoro generators on the primary vector. And matrix B with upper indices is just the inverse of the graph matrix, which defined in the products of vectors in the corresponding Fermat module. Yep. Maybe you are right. Sorry. Yeah, that's right. And I'd like to explain this by considering these trivial vertex. So it's just one structure constant. Thank you. Okay, and graphically, the one-point conformal block on the torus can be given by this tadpole diagram, which can be understood as follows. This is quite similar to the way we consider one-point torus functions. Indeed, it can be built starting from a CFT on a plane, then we conformally map the plane to a cylinder, and then identify edges of the cylinder to obtain a torus. And to find this tadpole diagram, we also consider trivalent vertex on a plane, and then identify edge states of two external legs to produce this loop. So the loop is for exchange channel, and this external leg corresponds to the primary operator. Now we see that the function of torus block depends on three parameters, including external conformal dimension, exchange conformal dimension, and the central charge. So we consider various regimes of how conformal dimensions behave themselves with respect to the central charge. And we distinguish between four types of blocks. The first block, first two blocks actually, are related to the case when we choose two conformal dimensions to be light. It means that they are not related to the central charge, and when the central charge tends to infinity, they remain fixed. So there are global and light blocks, and the global block is related to SL2 subalgebra or Virasoro algebra, while light block is related to the leading asymptotic and the so-called C-recursive representation of torus block. Another option is the heavy light block, when one of operators is heavy and the other one is light. And in fact, it can be shown that there is just one heavy light block, because related to the following choice, the external leg is light and the internal loop is heavy. The opposite option does not exist, just because the expansion coefficient of the torus blocks already first coefficient has a pole in the exchange dimension. Okay, and in particular, it means that there is now this so-called vacuum approximation, which was instrumental in calculating the entanglement entropy on a sphere, because we cannot set this loop to zero, contrary to vacuum blocks on a sphere. Another semi-classical block is the classical conformal block itself, and this is the case when two operators are heavy, so the respective conformal dimensions grow linearly with the central charge. And in particular, it's interesting to consider the case when the loop or the dipole diagram is much more heavier than the external leg. In this way, we obtain the linearized classical conformal block, and some later will show that it's this linearized classical conformal block which can be realized holographically in the formal ADS. So our point here is that all these four types of semi-classical torus blocks are not quite independent, and instead they are linked to each other by a chain of connections. So now let us start from considering global torus block, and we know that Virasoro algebra of a CFT living on arbitrary Riemannian surface has a finite dimensional subalgebra SL2. So the global block, by definition, is just the block associated to this SL2. Okay, we see that it does not depend on the central charge, and in fact, global block is just a d-dimensional conformal block restricted to 2 dimensions. Okay, in this case, the general expression for the quantum block drastically simplifies, and the corresponding expansion coefficient are given by these matrix elements, where instead of all Virasoro generators we have only L-1, L+1, and L0, which is just the commutator of this L+-1. So these three generators form SL2 subalgebra. And expansion coefficient can be explicitly calculated and shown that they can be packed into the hypergeometric function of this form, multiplied by this power law prefactor. And as a consistency check, we can consider the limiting case when the dimension of the external leg tends to 0, and in this case this global block is just given by this expression, and we see that this is the character of SL2 algebra, and the form of this function indicates that there is just one state on each level of the corresponding SL2 module. Now, the most important thing about global block is that it satisfies the second-order differential equation given here, and we would like to consider the regime where conformal dimensions tend to infinity in a coherent manner, meaning that we introduce some large parameter kappa, and the sigma and sigma tilde are just with scale conformal dimensions. So from the general theory of differential equations, we know that in this case the solution exponentiates like this, where function g is given formally by this integral, and actually this is very important result for us, because some later we will show that this exponentiated global block is directly related to the linearized classical block. Okay, another comment is that on a sphere, we already met this kind of second-order differential equations, which are just the so-called Casimir channel equations, and actually the appearance of this second-order equation is not occasional. Okay. Now we consider another semi-classical block with light operators, and it is the light-torus block, and in general it can be defined as a linear asymptotic of the quantum Virasoro block, and the central charge tends to infinity. And in this regime, by the way, we just it diverges in this limit. We just moved it on the left-hand side to single out the finite part of the conformal block. So this leading asymptotic is the light block, and the most important thing about light block and global block is that they are related to each other by the relation of this kind, where function phi is the standard Euler function which defines a particular Virasoro character. And having this prefactor 1 minus q says that global and light block are different by this prefactor, which is truncated Virasoro character. Okay, a few comments are in order. So, first of all, this light block in one-point case is the leading asymptotic for the so-called serecursive relations which define one-point quantum torus blocks. And another important observation that this factorization property actually is general for any Riemannian surfaces and for blocks with arbitrary number of operating insertions. So in the sphere case, global block and light block are equivalent, equal to each other, and following results of these offers, we now know that the sphere case is an exception, but in general, light block and global block are related by this relation. Okay, now we would like to use the symmetry argument and show that all the semi-classical blocks are related to particular contractions of the Virasoro algebra. And as I have already noted, the conformal blocks are model independent, they are completely fixed by symmetry algebra, and it means precisely that any semi-classical blocks that follow from original quantum block should be somehow related to operations done with the symmetry algebra. And indeed, this is the case, and to this end we consider, first of all, the Virasoro algebra, which is given by these standard commutational relations, and as we consider also primary operators, here we give how the primary operators transform under Virasoro transformations. So now, let me remind you what the Inonu-Wigner contraction is. So this the kind of limiting operation, if you have an algebra, and this algebra is parameterized by some small parameter, then you can send this parameter to 0 to obtain another algebra. And a canonical example here is how Poincare algebra is related to ADS algebra, or Galilean algebra is related to Poincare algebra. So in first case we have cosmological constants, so we can with scale generators of ADS algebra will help this cosmological constant and then send it to 0 to obtain Poincare algebra. In the case of Galilean algebra, this is just the speed of light, and sending the inverse speed of light to 0, we obtain Galilean algebra from algebra. So in our case, Virasoro algebra is parameterized by the central charge. So sending to 0 the inverse central charge, we can study various contractions. Okay, consider now general rescaled Virasoro generators, which are given by this expression where gamma is some function of integer parameter m. Then we distinguish between two main choices. when the Virasoro generators are rescaled in this way, it means precisely that the finite dimensional part of Virasoro generators remain intact, while other operators, other Virasoro operators are rescaled into different ways. So, since we also consider primary operators, we can show that this transformation law reduces to this general relation saying that the primary field is still SL2 primary field, but with respect to these higher order Virasoro generators, it's just a singlet. Okay, and doing these constructions, we observe that in the first case, the Virasoro algebra decomposes in two parts. The first part is SL2 subalgebra, the other part is infinite dimensional abelian factor, and this is expressed by these two lines, and we see that the whole contracted Virasoro algebra is just a semi-direct sum of SL2 and this infinite dimensional abelian factor. In the second case, this contracted algebra now contains, instead of abelian factor, the Heisenberg algebra, which is given by this H with the respective commutation relations. So, for these two constructions, we have two contracted algebras, which are both semi-direct products of finite dimensional SL2 and infinite dimensional factor, which is either abelian algebra or Heisenberg algebra. So our main proposition is that light and global blocks are just associated blocks which can be calculated using these two contracted algebra. In the first case we obtain a global torus block, and in the second case we find the light torus block. In particular, it's clear why global block is related to singling out SL2 subalgebra. This is because we consider irreducible representations, and it means precisely that this infinite dimensional abelian factor is trivially realized. It's not the case for the Heisenberg algebra, and calculating the associated block gives rise to that prefactor related to Early function. Now, we consider one more semi-classical block, which is the heavy light torus block, and as I explained earlier, one of dimensions, external dimension is light, while the loop is heavy. So the corresponding heavy light torus block can be explicitly calculated up to high enough order in the modular parameter, and it's given by this inverse Euler function. So it's also, thank you very much, it's also not independent, and we can show that the heavy light block is just a limiting case of the light block. So considering the light block and sending the internal dimension to infinity, we reproduce this heavy light block. So also we observe that since the heavy light block does not depend on conformal dimensions at all, it's just a zero-point block or Virasoro character. And this situation is quite similar to what happens on a sphere, where these relations are observed for 4-point blocks and 5-point blocks. Okay, the heavy light block also admits this Virasoro contracted algebra interpretation. In this case, we rescale all Virasoro generators, including the SL2 part, and show that the contracted Virasoro algebra commutation relations in this case take this form, which up to linear transformation, changing the basis, we can cast this commutation relation into the standard Heisenberg algebra commutation relation form. So, calculating associated conformal block, we arrive exactly at this expression. So up to now we considered 3 different semi-classical blocks, and they are all related to particular Virasoro algebra contractions. Finally, we consider the so-called torus conformal block, classical torus conformal block, and in this case all operators are heavy. So the respective dimensions grow linearly with the central charge, and we can substitute these dimensions into the conformal block and expand the resulting function around the infinite value of the central charge. So in this way we obtain some Laurent series, which has a principal part, which has a regular part, and the respective coefficients are just some formal power series in the modular parameter with next level expansion coefficient being some rational functions of classical conformal dimensions. And the most important thing about the classical block is that at large C the principal part of this expansion goes to zero. Less obvious is that the regular part exponentiates, and it follows that the one-point torus block is asymptotically equivalent to this expression at large C. All with respect to exchange dimension. Okay, so we see that we have four types of semi-classical conformal blocks, and three first blocks, which are global light and heavy light blocks, are just limiting cases when we send the central charge to infinity, while the classical block is the large C asymptotical, the original quantum block. Unfortunately, there is no any interpretation in terms of contracted Virasoro algebra, but I believe that there should be kind of deformation theory with respect to small inverse charge, starting from some contracted Virasoro algebra, which takes account of all these corrections in the central charge. So this is not done yet, and actually I believe that up to now we consider classical blocks as a kind of asymptotic expansion around infinite central charge, but there should be some symmetry algebra, Virasoro algebra formulation in the spirit of these contracted Virasoro algebras. Now we consider the linearized conformal block, and to this end we introduce this whole lightness parameter, which is just the ratio of two conformal dimensions, and then changing from the original classical conformal dimensions to delta, the lightness parameter, and the external conformal dimension, we can reorganize the whole conformal block function in terms of the double series expansion in delta and epsilon tilde, and most linear in the external conformal dimension. So instead of the power series in the modular parameter, for the linearized conformal block we have these two terms, where the second term is given by power series in the lightness parameter, while the expansion coefficient are just some rational function of the modular parameter. So this is the point where we should recall about the global block, and we conjecture that exponentiated global block is equal to the exponentiated quantum block, that is, it is equal to the linearized classical block. So recalling that function which appeared for the global block, we see that modular this logarithmic contribution, these two functions just coincide. And the most important thing about this conjecture is that for the global block we know some formal integral representation, which is given here, So we conjecture that the linearized conformal block on a torus in the one-point case is given by this integral. And finally, let me comment that this relation is analogous to what happens on the sphere case for 4-point blocks and 5-point blocks. Now we realized linearized conformal blocks in terms of particular geodesic networks stretched in a three-dimensional bulk, and we see that we can show this explicitly, that taking this tedpole diagram of one-point conformal block on a torus, we arrive at particular tedpole geodesic diagram embedded into the thermal ADS space, where thermal ADS is just the usual ADS space with periodic time. And the block length correspondence in this case claims that the linearized conformal block is equal to this sum of three terms, where last two terms are just length of this external leg and a loop, and the first term is just the gravitational action evaluated on the formal ADS background. Okay, so just to remind you what the formal ADS is, it's given by this metric where tau is the modules and coordinates, time coordinate is periodic with this 2-pi period, and the radial coordinate runs from 0 to infinity, and at infinite